Hello, welcome to another edition of Mathematical Games. I am Ed Pegg Jr., and I've been discussing a series of items based on the works of Mathematical Games, who wrote a column called Martin Gardner, who wrote a series of columns called Mathematical Games in Scientific American. And that was very um, inspirational for young people like me, and I became a mathematician, mostly because I was able to learn so much through recreational mathematics. Martin Gardner talked about pi, circles, and spheres quite a bit in his columns. I didn't do a compilation this time, but let me get into things. I decided to pick this topic because of Pi Day. I figured this could be a yearly thing where I try to keep updated. Of course, we have many demonstrations that involve circles, pies, and spheres. Here's a few of them, and I'll be showing some of them. And one cute thing I showed last year, if you take the numbers 1, 2, 3, 4, 5, and you square them, those numbers give the letters for Pi Day. And one note that's often mentioned is that it suffices to memorize pi to 768 places because that's where you get 9999999. So I myself have not memorized pi past, I think, about here. And I know a mnemonic, or at least I used to know a mnemonic, but I think I've forgotten the mnemonic. Now I would celebrate in poetry, trying the great. I forget how it goes from there. So here's one way of showing pi as a curlicue fractal. We basically assign each number to an angle, and it turns out that these odd patterns develop that don't seem quite random. It seems like a a um, a tangle that might be doing something. These curlicue fractals, you can figure out the heat of a curlicue fractal by how far it's spreading out as you continue it. And it turns out that certain values have a lot more heat than others, and many of them have interesting meander patterns that tend to repeat. One thing I didn't expect was for the Pope to release a statement for Pi Day that is filled with math jokes. You can there's a link for this if you go to the YouTube section. I put the link to my post on community, or you can just go to community.wolfram.com and see the notebook for this chat, and there's links for everything. Pope Leo the 14th has many math jokes in his statement. For example, he talks about manifold challenges and the digital sphere. It turns out that before he went into religion, he was a mathematician, got a degree in mathematics. He's our first mathematical pope since, I can't remember the name of the other pope who's a mathematician, but the first one in a while. One pi trick that I rather like is this trick done with e pi and the square root of 19. You can take that number, add 24, take the 24th root, and calculate it to 11 places, and you get this value, which is the same as the root you get for x to the third equals 2x plus 1. And you get this value, which is identical for at least 11 places. It turns out that this is in a realm of mathematics called modular forms. the same sort of thing that proved Fermat's last theorem. And modular forms are said to be very complicated, but they're almost magical when you can get them to appear. This is one of those cases. These this relation of this number with this root is in the realm of modular forms. And one thing you can do with that root, and I'll show it right here. Here's the root. You can use that algebraic space for disks, and here's the disk in the algebraic space. And just using that root, we get the Melanson 12 disk covering, which is related to e pi and the square root of 19 in a strange way. To almost 12 places, you get 12 disks covering a sphere, or covering a circle. And this is the optimal packing for 12 disks of the same size. So I thought this particular value might be called Melanson's constant. You can do a similar trick with e pi and the square root of 163, as noted by Ramanujan. But if we add 24, take the 24th root and go to 33 places, we get this value, which is very close to this related root. X to the third equals 2 times 3x squared minus 2x plus 1. This is a innocuous looking polynomial, but it agrees with this value to 33 places. I don't know of a geometric trick that can be done with it, similar to the 12 disk covering, but it might be in the 24th dimension. But I haven't figured out how to do that yet. Here's something else I found a while ago. 7 to the 7th over 4 to the 9th is very close to pi, to 5 decimal places. And that's pretty good since I'm only using 4 digits to do it. A related item is to figure out how to do strange tangencies. You can do this with a set of circles against a wall if you use the golden ratio, and you can do it with 5 coins if you use the Fibonacci constant. I did some explorations to go further, and those were the only 2 constants that popped out. The others are stranger numbers. So with this concept of tangency, we can start with a normal packing of circles where each circle touches 6 others. Doyle looked at transforming those to get new mappings, and they are now called Doyle spirals. So here's an example of one here. We've got a whole bunch of circles spiraling into infinity. And this is a resource function called Doyle spiral. We've got a variety of different things you can do with this set of transformations. By changing the transformations, you get a different picture. So here's another one that has 2 eyes that are being circled into. A lot of these happen in fractals, in particular the Mandelbrot set. If you look at Mandelbrot zooms, you'll see a lot of items like this because the transformation, which is mentioned up here, this transformation also happens in the Mandelbrot set, which is also done on the complex plane. These are transformations on the complex plane translated back to normal Euclidean coordinates. So here's 2 different spirals, and if you go to the long tail of the Mandelbrot set, you'll see a lot of things like this. And here's another similar item. And we can do more things like this. Excuse me. So this is a related transform, and this is one I want to look at more closely because I've known of this for a while, but I've never really done anything myself. I've just looked at the code of other people. But basically this code here, oops, this code here is using this sort of transformation. So I want to look at this further. There's also a way of going back and forth from circles to lines. And I'm working on a piece of code to do that right now because I want to do the full set of tangencies for lines and circles in one piece of code. But I'll be showing that a little bit later, but I still don't have it quite working with all the different line circle combinations. One famous circle is the Conway circle. So basically you start with you start with, let me bring this back. There's all the code for it. You start with a triangle and put a circle around it, the circumcircle, and then you take this green edge and you add that as an extension to the other two legs. And the same with the blue edge here, you extend the other two sides with it. And this red edge, you extend the sides of the opposite two. And those 6 points happen to make a circle, as noted by John Conway. And this is called the Conway circle. Now, one thing I wonder is if the circumcircle of the Conway circle is related to Steiner chains. That's something for me to look at. It would be amazing if that did happen. These are the sorts of things that, excuse me, that go through my mind all the time. Is this related to that? And usually it's no, but when it does, that's when I make a nice discovery. The circles of Descartes, we've got, excuse me, we've got the curvatures of circles shown here. A curvature is 1 over the radius. So this circle here has a radius of 1/11. This one here has a radius of 1/14, and this one here is a radius of 1/15. If you square those values and do the subtraction of minus 6 squared, this is a negative curvature. So that indicates an inner tangency. I believe that this will hold right, and so this would be 11 plus 14 plus 5 minus 6 squared equals the squares of all those times 2. And that's the property for 4 mutually tangent circles. All of these values here fall into one of 4 buckets modulo 12. And that always happens with these Descartes circles. You can get different buckets, and all possible values mod 12 occur, but they only occur in a select set of sets of 4. The maximal number of moduli mod 12 you can get is 4. So this has been known for a while, and it turns out that this property of the square of the sum is equal to twice the sum of the squares also happens with the complex coordinates. And using both of those facts together, you can do these mappings to get all of the various circles in a branching tree. And they're also named after Soddy, who's more famous for discovering a whole bunch of things about isotopes, for which he won the Nobel Prize. But he also wrote this poem, which was mentioned by Martin Gardner in one of his columns on this topic. One nice fact about the circle is that if you take any regular polygon with an edge length of 2, the annulus, the circle of the inner and outer radius for that polygon, is equal to 2 pi, is the area of the green and also of the red. And that happens for any polygon, any regular polygon. The one related item for circles is the Euler line. So here's a triangle here, and we're going to look at the circumcenter, which is the center of a circle bounding the triangle, the centroid, which is the center of gravity of the 3 points, the 9-point center, which is based on the 9-point circle, and the orthocenter, which is the intersection of the altitudes. And this is a particularly nice triangle because those 4 values are nice coordinates, -2, 0, 1, 4. And it turns out that these 4 values are always in this particular ratio. So I thought it would be nice to actually get coordinates that showed that automatically. There's also a hyperbola dealing with that. And here's a diagram showing all these. We've got the 4 points here, the circumferential, centroid, 9-point center, and orthocenter. The 9-point center is in brown here. In fact, let me try to bump this up to not be nearly invisible. Where's my... Let's change that to not be thin. What happens then? Oops. I need to evaluate these first. And now this should run. All right, so this is a little bit clearer now. So we've got the circumcenter here in the middle of this circle. I should make this triangle thicker here. Where's my triangle? Oh, it is thick already. Oh, well. So the triangle is in black here. The circumcircle is in red. That has the vertices of the triangle. The 9-point circle is here. We've got some of the points are these intersection points of the feet in green lines. We've got the 3 feet in green, making right angles to the edges. We've got the centroid, which is the center of the medians, the 3 medians of the triangle. And in red is the circumcenter, which is the perpendicular bisectors. and that is the center of the circumcircle. And the 9-point circle, if we take the midpoints of the segments to the orthocenter, so here's one midpoint, another midpoint, another midpoint, and also the intersection points of the medians and the feet, those 9 points make the 9-point circle. And that is centered here. We can also do nice things like the Dirac hyperbola, which is shown up here and through here. An E circle is an X circle is also called an E-scribe circle. And those are circles that are on the outside. You've got the in circle on the inside. The X circles are on the outside, also tangent to the same 3 lines. And it's these lines that I'm looking at for a program I'm doing with tangencies with circles and lines and everything else in 2 and 3 dimensions. So here's a 3-dimensional case that shows the Exspheres. This is the Exspheres function that I wrote. And here's the program, the circles of Apollonius. I originally called it a tangent sphere, similar to circumsphere and insphere, which happens to also do incircle and circumcircle. But we've decided to use the global sphere to indicate objects that will work in multiple dimensions and for both circles and spheres. So if we take 3 circles, can we draw a circle tangent to all 3? That's the problem of Apollonius. And it turns out there are 8 different solutions. So I've got 3 circles here, and here are the 8 different solutions. And one thing to consider is whether the circle is on the inside or outside. So for this yellow case here, all 3 circles are on the outside. For what color is this? This purple here, all 3 circles are on the inside. And if you do different combinations of inside and outside, you get a total of 8 different solutions, as shown here. And we can go to 3 dimensions, and in there are 16 solutions. So here I showed 2 of the solutions randomly. I'll just, let me evaluate this code here. So now, why isn't working now? So now, here are 2 of the 16 solutions shown. There's unfortunate things that happens if I try to show all of them. I'll just give an example. There's just a cloud of bubbles here. You can't actually see anything inside, despite the fact the opacity should be low enough. So 2 at a time is pretty safe. And as I rotate it, note that often one of the spheres will just vanish. Of course, now it's not happening. So there's 2 of the solutions for Apollonius in 3D. And I want to try to get this working for a mixture of planes, spheres, circles, and lines. So while I'm going through the demonstrations, I'll often hit things I've either forgotten about or I never bothered to actually memorize in the first place. So one of them that was new to me as I saw it again was the eyeball theorem. You've got two circles of different size that don't intersect, and you draw tangencies between them. The two different chords that are struck out happen to be the same length. And this is what's called the eyeball theorem. The Fermat point of a tetrahedron minimizes the total distance to the vertices. So here's an example of a tetrahedron, and the Fermat point of this set happens to be this, and we can check that. And we can check that with simulated annealing. Everything here is basically 0 because this is 10 to the minus 115. So with chop, this would vanish to 0. Now we can take the sum of distances to the Fermat point and make the Fermat tetrahedron, where basically we extend all of the lines of the central tetrahedron through the Fermat point. And how much are these extended? That has to be the sum of the distance. Right. We take the sum of the tetrahedron from the vertices to the Fermat point, and we take that total length and extend all of those lines out. It turns out that those lines are tangent to the circle tangencies through the Fermat point. And this is also a property in 2 dimensions. That's something I've often wondered about how that winds up working. I've wanted to use that as a method for finding the Fermat point, which is a very difficult calculation. I don't know of an easy way of calculating it. This is basically a brute force method for finding it. So I'm wondering if there's something that can be done to simplify this particular problem. We can also take a look at circles in different dimensions. So here's an example of circles on a icosahedron. These are actually done with splines instead of geometric circles, because we don't have pure circles working as a geometric object in 3 dimensions. So this is a way of faking it with splines. The Johnson circles shown here. Here's a picture of the Johnson circles, are congruent to the circumcircle of the reference triangle. So if we go through the orthocenter here, which is the intersection of the altitudes, and we draw the circles through 2 vertices and the orthocenter, we get a set of circles that have equal radius to the circumcircle. And it happens that the centers of those 3 circles also make a circle of the same radius as the circumcircle. So we've got the Johnson circles through 2 vertices and the orthocenter, the circumcircle through all 3 vertices, and the circle through the Johnson centers here all have the same radius. And thus the set of Johnson circles. Another tricky problem is the Kinmotu circle, where we've got a triangle and we want to draw squares of the same size, each with 2 vertices on the sides of the triangle and all intersecting at a point. That's the Kinmotu problem, and the answer leads to the Kinmotu circle. And this is a nice demonstration showing that. The Loeschian spheres are a 3D analog to what's called Ford circles, where you take Ford circles are where you take the fractions 1/2, 1/3, 1/4, the Ferry sequence, including numbers like 2/3. If you draw circles with those radii and put them at the locations on the number line, you get a bunch of tangent circles, which is something I should have shown here. Then 3 dimensions, you can also do that, and you get what's called the Loeschian spheres, which is what I'm showing here. All of these spheres are tangent to each other, and they all have particular radii similar to a Ferry sequence, but it's a little bit more complicated. It's called the Loeschian numbers, and they are numbers of the form x squared plus xy plus y squared. For example, here's a set here. 4 squared plus 2 times 4 plus 2 squared is a Loeschian triplet, 28, 2, 4. With these triplets, you can plot locations of the Loeschian spheres on the complex plane. And I show the locations of them here. Another odd circle is the Lucas circles, which are circles that are mutually externally tangent to each other and that are also internally tangent to the circumcircle at the vertices, as shown here. And they intersect, as shown. We've got the points of tangencies, and they are internally tangent to the circumcircle of a reference triangle, as shown here. This is something I want to go into further for the function we have on triangle circles. There's, I think we list 20 circles there right now, but I know there's a lot more. The Malfatti circles were once thought to be the best way of carving circular columns out of marble, but it turns out that they are never the correct answer. The correct way of doing it is just to take the end circle of a triangle and then to do the best with what's left. But this concept of the 3 tangent circles is still a nice looking item. Miquel's theorem is if you, let's see here. I forgot what that point is. Oh, it doesn't matter. Let these be points. All right, we can take any points in green. Right, we can adjust these points in any way. So if we put any points on a triangle's edges, there will always be a corresponding point for what you picked on the triangle edges. And this is Miquel's theorem, the fact that these circles will always intersect at a point. He also found what's called the pentagram theorem, where if you take any pentagram and you draw circles through the circumcircles through the different triangles, if you take the ones that are not on the central pentagon in black here, these are the points that are outside the pentagram, those will always be concyclic. and that is Miquel's pentagram theorem. Mixed linear circles are tangent to the two sides of the triangle and also to the circumcircle, as shown here. We can also look at what Schmidt looked at for circle tangency, where he looked at curvatures in a series and found what's called Schmidt arrangements based on quadratic fields. And here is the Schmidt arrangement for the Gaussian integers here. We can zoom in on these by adding more circles, and they get more and more complicated. And certain values lead to nice quadratic fields with different properties. For example, a -2, I forget who the Greek person was who proved the square root of 2 was irrational and he was thrown off a boat and killed. But that person, I believe, should have the square root of 2 named after him. And this quadratic field is based on that. The Heegner numbers, 1, 2, 3, 7, I know 67 and 163 are in them, lead to particular different strange geometries in the complex plane. And 163 is the last of the Heegner numbers. If you have dealt with 6, 7 as a meme, 67 is one of the important Heegner numbers. And I'm trying to find some nice geometry to show that, but I haven't gotten it yet. The next Heegner number is based on 3, and here's the Schmidt arrangement based on the 3 geometries. And 7 is a Heegner number. So here's the Schmidt arrangement for 7. And 11 is a Heegner number. And we get this pattern. And also 19 is a Heegner number, where we see these sorts of patterns happening. So for each of these Heegner numbers, I'm hoping to find nice pictures to go with each one, and the Schmidt arrangements are one method for doing. So I mentioned Steiner chains earlier. So that is in certain cases, if you have two different circles, an inner circle and an outer circle, no matter where you start drawing two tangent circles, you'll end up with a chain that wraps around. And it's possible to have two set Steiner chains where it loops around twice before you get back to the tangency, but we don't show that with this one. I need to explore the math of this to figure out exactly how these work, since I don't quite understand this yet. But this is something I'm hoping to look at sometime soon. For example, does this relate to the Conway triangle I showed earlier? Here's one example of an experiment I looked at. So this is called the Taylor circle. We take the altitudes of a triangle, and then we drop a new set of altitudes from those 6 points, from those 3 points, and we get 6 points. Those 6 points are concyclic, which is shown by Taylor. And here's an example where we do that. So as an experiment, I wondered, well, what happens if you go another step? So that's what I did. I was thinking that these extra points might make more circles, but they don't. They don't do anything. But this is an example of me trying an experiment, and usually it doesn't lead anywhere. And this is one example, but here's a picture of it. The Villarceau, I'm not going to try to say that. If we take a torus, there's two obvious circles you can make with a torus going through a particular point, but there's also two slanted circles that are less obvious. And as we change what the point is, the four different circles through the torus that go through that point change. Villarceau circles, maybe? I'm probably saying that wrong. One thing I tried to find this week was there's a famous quote that somebody said that they would never fault a person for mispronouncing a word because that showed that they learned the word through reading instead of hearing it. And I do a lot of reading. There's a lot of words I don't know how to say. No one has ever mentioned these circles to me in conversation, unfortunately. The Wallis sieve is one way of hitting pi. Basically, we start with a square, we take out the middle thirds, then the middle fifths of what's left, then the middle sevenths of what's left. And if you keep doing that, you'll get a shape. The what's left has the same volume as pi. And this was something noticed by Wallis, I think, 300 years ago. And you've got this series approximations. It turns out that we can expand this up to 3 dimensions. And here's the equation. If we take this series in 3 dimensions, we get something that converges to pi. And if we combine them in the right way, we can make a Wallis sponge that if we take the middle thirds out, then the middle fifths, then the middle sevenths, and continue on middle ninths, that will come up with an object that has a volume of pi, similar to the Menger sponge, but it's the Wallis sponge instead, because we're not taking out 1/3 each time. We're taking out smaller and smaller fractions. So this is a very slow graphic to make, so I tried to speed it up. This code here is relatively zippy, but I haven't figured out how to do the inverse of this quickly. So I'm still working on how to speed up this code. I know we can do this with regions, but that generates an order of 1 million cuboids to do this particular graphic, and that's kind of slow. So I'm trying to find a faster way of doing it. There's a couple items with circles that are not named after a particular person. So here's a problem with chords. Through a point, we draw 3 chords. So here's 3 chords, black beating these points here. And with these chords, we draw 3 circles. A brown circle, a green circle, and a whatever color that is, chartreuse circle. Another strange fact I recently found out, there are 5 named colors on the rainbow that don't involve red, orange, yellow, green, blue, indigo, violet. And one of them is chartreuse. Another is harlequin at 552 nanometers. And also there is cyan. There's not many other pure spectral colors on the rainbow. So those circle intersections are on a line. If for any 3 chords, if you connect up the intersection points, they will form a line. One nice little fact is if you have a inscribed quadrilateral in a circle, the opposite corners always add up to 180. And I forget this fact over and over again. So I thought I'd put it here as a reminder to myself. A similar object is the 6-dis theorem. If we make tangent circles, 6 tangent circles within a circle, the opposite tangency points will always meet at a single point. We can also look at, not sure why that's not packing. Why is that only showing one sphere? Let's try reevaluating this code. Probably a variable is upset somewhere. So this is supposed to be showing a sphere packing, but I won't risk closing down my Mathematica so I can get this to show. The densest packing of the spheres has been proven to be, I forget which one of these it is, face-centered cubic, I believe. And that was a long proof in Coving, but it's finally been accepted that this idea of Kepler, that was the densest packing, was the best, but it took Hales a long time to get that accepted through various program provers, theorem provers, just because the proof he had was so complex. But now that proof has gone through a whole bunch of checks through computer teching techniques, that theorem is now accepted. Here's a picture of the 15 great circles on a sphere. These relate to the hexachus triicontahedron. One study I did a while ago is lattice circles. So we have a lattice. I'm not sure how well these blue points show up, but we have a lattice of points, and we basically want to find all the different ways of drawing a circle through those points, and we recenter those on a central triangle with vertices 0, 0, 1/2, 0, and 1/2, 1/2. We can always move the points around so that it will be somewhere within that triangle. And it turns out there's a whole bunch of different distinct ways of making these different lattice points. And I was wondering if I could figure out anything about these different forms. And I ultimately didn't figure out anything of note, but I still compiled the results. I have several thousand results stored in this demonstration on lattice circles. Somewhere in here, I wonder if there's 7 is in here. There's a 7. I'm not sure of the first case that is not listed here, but it's always possible for any given number to get that exactly that number of points. But the circles can get very large if you say, pick the number like 719. Here's a simple theorem that I completely forgot about. So you have two different chords on a circle. If you extend them so that they intersect and then multiply, AB times AP is equal to DC times DP. This is a nice fact that I've forgotten many times. we can take a look at the best packings of circles, as shown here. Some of these are not proven yet. In fact, this is probably obsolete. I'm not sure which ones of these have been improved since I wrote this 10 years ago, but I'm sure some of these are no longer considered the best solutions. It's even more difficult in 3 dimensions. The Thales problem, I think, is the best placing of points on a sphere, and that's only been solved up to 12. But they have best solutions up to best known solutions up to thousands. Here's a cute one. We have a line on a semicircle. If we draw the 2 extra semicircles and then draw 2 tangent circles to the line of perpendicularity, those 2 blue circles will always be the same size. The one thing I've looked at quite a bit is tetrahedron centers. So here's an example of one, the in sphere. And I think on the next page, yeah, here's the 12-point sphere. We can draw the 3 tetrahedron involved in the calculation of the 12-point sphere. And the sphere is the circumsphere for all of them. And while I was doing this talk, I noticed that all my calculations for in-sphere look really complicated for tetrahedra. So I wanted to find a tetrahedron that had a nice in-sphere. And here's a solution. For this set of points, here's the in-sphere, and it looked quite reasonable. Usually it's an order 8. Each vertex is an order 8 polynomial. The reason for that is because the in-sphere is based on the face areas of the tetrahedron. So the only way it can come out nicely is if all the face areas of the tetrahedron are integers, similar to Heronian triangles, except that the edges could also be square roots. So I started taking a look at that. What is an example where all the edges have different lengths, but the in-sphere is rational? So it turns out, it turns out that's a very difficult problem. If you restrict the longest edge to 30 or less, there's only one solution if you need integer points. And this is the unique solution where all edges have length square root of 30 or less. I wasn't expecting that. And here's the 4 areas of the faces, 4, 5, 8, and 9. And I might as well close out with arcs. Here's a nice thing you can do with circle arcs with the 3-point arc function. We get the projective space 3, 2. Every point, every set of points is on an arc. So that's all I had. Actually, I have this one more thing. But first, let me show that this whole talk is available at our community place. You can go to community to see it. And one extra thing that we've got here is the haberdashery problem. There's a 3-piece solution that was found, and here it is. You can divide a square into 3 parts and rearrange them to make a triangle with a hole in it, which is not known until just recently. So that's my talk. Many thanks for listening. to the YouTube chat once I find it again. Just a second. All my links are being hidden here. Okay. Yes, if anybody has any questions, just paste them into chat. I'll be glad to answer them. If I can see them. All right. I think I'll close it there. Many thanks for attending my talk.